Welcome to this workshop about A/B testing for data science. My name is Carlos Afonso. I'm one of the data science instructors at New York City Data Science Academy. Just a brief introduction about myself. I have a diverse background. I first studied physics. I have a master's in physics engineering. After that, I got interested in biology, so I ended up actually conducting biomedical engineering research at the University of Oxford in England. I was doing research there towards a PhD. I didn't finish that PhD because I actually moved to industry, and I spent 4 years working in a corporate consulting, solving data science problems and machine learning problems for large companies in the world, mainly here in the US. So more recently, I've started teaching. I'm now using my experience both in academia and in industry to teach students like you how to learn data science and how to break into the data science field and hopefully get achieve the career goals that you may have in data science. So today, this workshop is going to be about A/B testing, and particularly about using permutations. It's a method that helps us better understand what is A/B testing and what are the main concepts behind A/B testing, of course, in the context of data science. So let's start today's workshop. So this is the outline for today. We're going to cover A/B testing and permutation test. So those are going to be the two main sessions. At the end, we'll have a coding session using the R programming language. And at the very end, we'll have a Q&A session. So normally in our classes, in our bootcamp, we have small groups of students, and it's very interactive. And I would open the conversation to all of you in that small group that we normally have in the classes. But I see that we have so many people here right now. It's going to be impossible to have the open conversation with all of you, with the open mics and so on, and asking questions as we go along. So I'd ask you that you take note of your questions for the end. The idea here is to explain the concepts very well. So hopefully the questions that you may have will be answered as we go along through the presentation. However, if they are not answered, write them down and save them for the end. And at the end, we have a Q&A session. Feel free to also use the chat to ask immediate questions you may have about what we are covering at the moment. But keep in mind that that question may be answered the slide right after. So the outline: first, we're going to talk about A/B testing, what it is and why do we use it. We're going to show talk about some examples of A/B testing. Then we'll cover in detail how A/B testing is done. Like, we'll break down the process into steps. And we'll come down to the idea of hypothesis testing, that it's necessary, kind of the final step in A/B testing. And we'll cover the main concepts involved in hypothesis testing, in particular, what is the p-value, the infamous p-value. For today, you'll learn very well what the p-value is. We're going to make the probability. We're going to show you the probability interpretation and meaning of the p-value, and we're going to use actually some graphical representation so you can have a better visual understanding of what the p-value is. Then we'll go into the permutation test as a way of actually doing the hypothesis testing part of A/B testing. Again, we'll cover what it is and why do we use the permutation test, and we'll break down the process of doing a permutation test also in individual steps. And in the end, we'll do the coding session in R, where we implement from scratch all the concepts that we learn both in A/B testing and permutation test. And so you'll see the details of the concepts that we learn happening directly in the code. And then we'll show you kind of a more general solution. And at the end, we'll even show you our Shiny app, an interactive app where we can play with all these concepts that we learn. Okay? And at the very end, again, we'll have the Q&A session. So the main learning objectives for today, I broke them down into statistics and coding. As you know, data science requires knowledge of statistics, knowledge of coding and programming, and also industry knowledge. So in this workshop, we're going to focus mostly on statistics, but also some skills in coding. The main learning objectives in terms of statistics is going to be understanding A/B testing, hypothesis testing, the concepts involved in hypothesis testing, in particular the p-value, and the permutation test, which is going to be using to do the hypothesis testing part of A/B testing. In coding, we'll see more briefly. Again, the main focus is the understanding of these concepts around A/B testing. But in coding, we'll see how to use variables in R, how to use loops, and how to use functions in R at the final session, coding session at the end of the workshop. Okay, so that's the outline for today, and those are the main learning goals for today. Right. So I'll still try to make this interactive. I cannot have you all answer directly. Would be, a lot of people replying at the same time. But I'll posing you questions, and I invite you to, think out the solutions on your own head. Feel free to write them in the chat, or if it helps you, take a pen and paper and write down the answers yourself. So it kind of helps you understand where your knowledge is at. What's your current way of understanding these topics, and hopefully you'll improve your understanding today. So my first question for you is, because you are all here and this workshop is about A/B testing, you're probably all interested in A/B testing. And it's very likely that you already heard about A/B testing. So my first question is, what is A/B testing? So I would invite you to think about currently what's your understanding of A/B testing. So what is A/B testing? You can just think it for yourself in your head, think it out loud, write it down in the chat, write in the paper. Just think, what is A/B testing? What's your current understanding of what is A/B testing? So I'll try to also keep an eye on the chat. All right. Experimenting, comparing one method against another, allow us to compare two different processes in order to find out. Okay, yeah, you guys are writing. Is technique to evaluate one or more options. Great. Control group versus treatment group. Good. Testing a hypothesis. A/B testing is testing one model against another, like two methods. Yeah. All right. To compare experiments to compare stimulus. Okay. Everyone seems to be going in a very good direction. All right. On a sample to see what effect it will have against the entire population. All right. So I see some people here may have seem to have a more advanced understanding of A/B testing. So let me just mention. This is a more introduction, so we're gonna understand the concepts very well, but we're gonna keep it at the more introduction level. And fancy name for t-test. We're actually gonna do A/B testing without doing any t-tests. So if you haven't if you don't know that you can do A/B testing without doing any t-test or any use any statistical theory, in particular any statistical test to the hypothesis testing, today you're gonna learn how to. So the permutation test is actually a more general method to solve the hypothesis testing in A/B test. You don't need to use a t-test. All right. Very good. So let's and why do we use? So why do we use A/B testing? It's kind of the same answer as to what is an A/B testing that you already provided. So a general answer for what is an A/B testing is an experiment to compare two competing options, and those we call them A and B. So very briefly, that's what an A/B test is: an experiment to compare two options, A and B. We call them. Okay. What are those options? They could be different treatments in the medical context. They could be different designs, for example, different advert designs, or different web designs in a more internet context. Or they could be different products, or even different prices for the same product to see which one would get more profit, and so on. So the options could be anything, depending on the different industries and the different problem that you are trying to address. So that's what an A/B test is. Now, why do we use the A/B test? Kind of the answer is kind of similar, and you already provided that answer as well. We want to determine if those two options are different. Okay, different how? More technically, we want to determine if they are different in a statistical sense. That's why we're going to need to do hypothesis testing and permutation test, and we can do the hypothesis testing with the permutation test. Now, that's the more technical part. The business sense, we want to determine if one of the options is better than the other. If one option is better for our business or for the problem, for example, in the medical context, if one treatment is better than the other for a certain disease. Okay. So the technical part is we want to check if the options are different, and we need to do the statistical testing and the hypothesis testing to determine that. In the applied sense, the more business-like sense, we want to determine what's the better option for our problem, for our business, or for other problems that we are trying to solve. Okay? And the better depends on what's the question, what's the goal that we have at hand. For example, within even a business context, you may have different goals. You may have the goal of acquiring new customers, or may have a goal of increasing the profit. Sometimes you may sacrifice, for example, profit with the goal of acquiring more new customers. So other times, depending on the stage of your business, you might focus more on the profit itself. So the A/B testing is a way of comparing two competing options, A and B. We want to check if they are different, not just if they are different, nor we want to check if one is better than the other. And it depends on what's the goal and the problem that we are trying to solve. Okay, Some examples. Okay, so can anyone provide some examples in the chat or sync out of examples that you may know or have may come across of A/B testing? They could be general, they could be specific. Any examples you can think of A/B testing where A/B testing could be used? Okay, you have the chat. Amazon changing, okay. Pick a color, marketing appeal to different ad campaigns, testing different website options, marketing campaign, very good, very good. This one website gets more clicks than other. Placebo against drug, very good. Yeah, very good. Call center campaigns comparing promotions. Coronavirus vaccine tests, very yes, yes. Very good. We have lots of very good examples. So let's, you covered some of the ones that I actually have here to share. So actually, the idea of A/B testing, comparing two options, is quite has quite an history, right? It's not just from now the area of the area of the internet and technology. It was used in the past in agriculture to determine, for example, given two different soil treatments, which one's going to be better for seed germination. So similar to the history of statistics, A/B testing also has a root in, for example, agriculture experiments to determine if two different soil treatments would have better seed germination. So it's not something new, it's old, and that's why we have all these statistical theory behind it. More modern examples, as you mentioned, two web headlines to check which one produces more clicks, or two web adverts, which one generates more conversions, or two prices, say for a product, which one yields a higher profit, or which one leads to more new customers. Again, that example I referred just before. The experiment is kind of, we are testing the same two options, two different prices, but the goal here is different. In one, we want to increase the net profit. In the other one, we want more new customers. So we would be willing to sacrifice, for example, the profit to get more new customers. And again, this depends on the business cycle, on the cycle you may be in your business. And of course, the examples from the medical context, two therapies to check, for example, which one may be more effective at suppressing cancer. And from the medical context comes these terms of control group and treatment group that someone mentioned in the chat already. And these are, instead of calling the groups A and B, we know in the medical context, normally we call them control group and treatment group. Even outside of the medical context, sometimes that nomenclature is also used. And what is the control group and what is the treatment group? Well, normally when we're comparing two options, and one of those options is kind of the standard option, the current option for which we already have information. And then the other option is kind of a new option, a challenging option that we think may be better. So the control group represents the standard option, or in a medical context, sometimes is the option of giving no treatment. So in medical context, you'll have two groups of people. One of them is going to get one treatment and the other is going to get a different treatment. But it's very common to keep one as the control group as having no treatment at all, or just having a standard treatment or a placebo treatment. That's the control group. Then the treatment group is the one that actually takes the new treatment that we think is going to be better. Better than what? Better than the control group, better than having no treatment or having the current standard treatment or having just a placebo treatment. So control group represents either no treatment or the standard treatment. The treatment group represents the new treatment, the one that we think is going to be better than the current. Okay. Here we're going to keep going with the A/B nomenclature. So keep referring to the groups as A and B. We'll not be using the control group and treatment group nomenclature, but you need to know that it exists and it's widely used because of the influence of the medical field. All right. So let me provide you some specific examples. Those were kind of general examples as you provided. So there's this famous one A/B test example from Microsoft, the Bing search engine, where one single A/B test, where they changed the way the Bing search engine displayed the headlines, led to a huge increase in revenue, 12% increase in revenue, just one A/B test. This is not very frequent. That's why it's so impressive. One single A/B test led to 12% increase in revenue of the Bing search engine. That is more than $100 million alone in 1 year, just in the US. So that was quite amazing. Imagine being yourself the one that came up with that A/B test and did that A/B test, and in 1 year you increased the revenue by $100 million just in the US. That's not the most common, but I'll give you some more other examples. Amazon. Someone referred the example of Amazon on the chat. For example, moving Amazon noticed that through many tests. Okay, that example from Microsoft is someone had an idea of an A/B test. The idea was there, and they were not doing it. And at some point, one of the Microsoft Bing employees decided to test it, and they found that huge result by testing just that one idea. Amazon certainly tests many ideas the same way as Microsoft does. And by testing many ideas, they found out that moving the credit card offers from its homepage to the shopping cart page when you are going to check out increase the profits by also tens of millions of dollars in a year. So you can see how these A/B tests can be powerful. Okay. However, they don't work all the time. Actually, most of the time, you don't get positive results, and certainly not positive in the sense that they are going to drastically change your business. So for statistics from both Google and Bing, only about 10 to 20% of the A/B test experiments generate some positive results. Okay. If you are interested in these examples, I'll leave you here the reference, and I'll be providing you with these slides after the presentation today. So you can read more details about these examples and others. All right. So now we come to the how. How is A/B test done? Okay. We have some action in the chat. Let's see. How does it, customer acquisition? Okay. Well, very good. So and again, I invite you to try to answer this question. Maybe not in the chat, it can be long, but think in your head. What's your current understanding of A/B testing? How is it done? If you had to break down A/B testing in steps, how would you break down the A/B testing process in steps? You can try to answer in the chat or just by yourself in your head, in a paper. What would be, if you had to break down A/B testing into individual steps, what would be those individual steps? I'll give you a minute to try. Okay, random sampling, hypothesis generation. All right. Where the idea is to try to break down the process in individual steps. Subjects of our data. Okay, I see. So now the answers are getting together. Random sampling of subjects or data. All right. Okay. So let's see a possible breakdown of the A/B testing process into individual steps. Okay. So I'm calling this one step 0. This is actually the process of coming up with an idea of an A/B test and defining what's going to be used and how the A/B test is going to be done. Okay. You need to have an idea of what you want to test, right? Like that Microsoft example, they had this idea of changing the way the adverts are displayed on the Bing search engine. You need to have an idea to test first. Okay. Once you have that idea, you need to define how you're going to do the A/B test, right? What's the question that you are trying to answer? What's your goal? What's the data that you can use? What are your customers that you can potentially use as your subjects? And what are the two options that you're going to test? And what's the way you're going to compare those two options? That's called the test statistic. Okay. So there's a step 0 that often is not talked about, but the very first step is actually having the idea that you want to test, and then defining very precisely what's that idea and what data can you use to test that idea. What's the exact goal in terms of the business? Could that improve your business? So you cannot just test an A/B test just for the sake of testing it. There needs to be a reason behind it, and ultimately the result of that A/B test could improve the problem you are studying or improve the business you are testing for. Okay, so that's step 0. You need to have an idea, and you need to define what's the A/B test that you want to do, and what's the data you're going to use, what's your question, what's your goal, and what are the two options that you're going to compare, and how are you going to measure the difference between those two options. That's called the test statistic. That's step 0. Okay. So let's start with kind of the individual steps after that. So once we have the definition of the A/B test, how is it executed? So step 1, we could say we need to have a group of all the subjects that we can use for the A/B test. So here representing as step 1, in this case, these illustrations representing 20 total subjects that we can use for A/B test. So these are step 1. We need to have a group of subjects, of individuals we can use for our A/B testing. In this example, we have 20 total subjects that we can use for our A/B test. Okay. The step 2, we need to separate those subjects into the two groups, the group A and B. And that separation needs to be done randomly. So the step 2 is randomization, is where we randomly assign the subjects to the two different groups, A and B. And I'm going to illustrate that by just randomly assigning these 20 subjects to these two groups, which are A and B. Okay, so that's supposed, well, that was very quick. So there you go, randomly assigning those 20 subjects into two groups, the group A and the group B. Okay. Step 3 is to actually expose those subjects in the individual groups A and B to those options, the option A and the option B. Here, the option A is represented with the color kind of purple, blue color, and the option B with the color yellow. Okay, you expose those subjects to the different options A and B, and you measure the result. In here, we're going to measure the result as a success or failure, like a yes or no. And green is going to represent yes, and red is going to represent no. Okay, so step 3 is to actually expose the individuals in the different groups to the different options A and B, measure the results, and compute the test statistic, compute the difference between the groups. So that's what we're going to do here. We expose the individuals in each group to the respective options A and B, and we measure the results. So we see now that from the group A, for example, we had 7 greens, so 7 yes, 7 conversions, 7 successes, 7 people that bought the product, 7 people that clicked in the ad, and so on. So 7 yeses. In group B, we had just 4 yeses, okay, so 4 greens. Okay, so the conversion rate, if you will, for A was 70% because it was 7 in 10, and the conversion rate for B was 40% because it was 4 in 10. The difference between the success rate for A and B is 70 minus 40, that's 30%. So our test statistic is the difference in the success rate between A and B, and the observed value was 30%. Okay? So that's step 3. We went from step 1, where we had all the subjects that were available for our A/B testing. We randomly assigned those subjects to the different groups A and B in step 2. Then in step 3, we subjected those subjects to the different options A and B and measured the results. We saw that the success rate for A was 70%, the success rate for B was 40%, so the difference between A and B is 30%. And that's our test statistic, the thing that we are using to measure the difference between A and B. Now the question becomes, is this difference of 30% between A and B in this problem statistically significant or not? Okay? And that's where we need hypothesis testing. So the hypothesis testing is the process of determining if that difference that we observed, the 30% difference between A and B, is statistically significant or not. And we're going to see that we can use permutation test to determine that. Okay? So we'll be covering the hypothesis testing in the next slides. I just want to refer then, again, another step that's often not mentioned is that I'm calling it the 5th step, where you need to make a decision and potentially take an action on the result from your A/B test. Okay? If you get the result that's significant, maybe you want to implement it in your business to improve your business, improve the profit, get new customers. Whatever the goal was in the beginning, you need to then make a decision. Okay, given the result of the A/B test, are we going to use that to apply it to our business, to apply it to our problem, to make it better in our business or our problem? Okay. So again, this workshop is more introductory level. We're going to be talking about these steps 1, 2, 3, and 4. We're not being covering the kind of step 0 of how to define an A/B test and all the process involved in defining the details of the A/B test itself. But we're going to describe this process of actually doing the A/B test and determine if the A/B test is statistically significant or not. Okay, so we saw the step 1, step 2, and step 3 here. All the subjects, in this case 20 subjects, just using small numbers so it's easy to see the process. We randomly assign them to different groups. We expose them to the options in each group, and we measure the statistics. Okay, and in this case we have a difference of 30% between A and B. That's our test statistic. Now we want to know if that 30% is statistically significant or not. Okay. All right. So this is kind of the summary of the result. We had option A and option B. We had a total of 10 subjects in each option. For option A, we had 3 no's. Okay, so option A here, we had 3 reds, 3 no's, and we had 7 yeses. So the yes rate was 70%. For option B, we had 6 no's, we had 6 reds, and only 4 yeses. So the success rate, the yes rate, was 40%. And our test statistic is, we define the test statistic here as the difference between the yes rate between A and B. So A minus B, 70 minus 40, that's 30%. Now we want to know if this 30% is statistically significant or not. And we want to know if that difference, if this 30% difference could be due just to random chance, or is actually due to a real difference between the options of A and B. Okay? Again, in this example, we'll be using small numbers, like and small and round numbers, so that everyone can follow along and you can do the math in your head as we go along. Okay. So another perspective to help you understand the process, this is not necessary, but if it helps you understand the process a little better, throughout the A/B testing, we don't need to follow individuals throughout the whole process. But in this case, I'm showing the process of A/B testing through the lens of a single individual. So for example, we had this first individual that was in the whole pool of all the subjects, and through randomization, it was assigned to the group A, and then we exposed it to the option A, and it was a success. So it was a yes. He clicked on the ad, he bought the product, or so on. But for example, another individual, this one was also randomly assigned to group A, was exposed to option A, and it was a failure, was a no. Okay? A different individual was randomly assigned to the group B, and then exposed to the option B, and it was a yes, was a green, a success for group B, and so on and so forth. So this is showing you the perspective of a single individual that participates in A/B tests, so you can better understand the process, even though when we just think about the A/B test, we think about it more in terms of the whole process. We have all the subjects, we randomly assign them, we expose them to the options, and we measure the results. This one is just to help you understand the process through the lens of a single individual that's involved in the A/B test process. Okay. All right. Let me just check the chat for a moment. Okay. All right. Very good. All right. So now we need to determine if this observed difference of 30% between A and B is statistically significant or not, and that's the hypothesis testing part. Okay. So the hypothesis testing, we want to determine if the difference is statistically significant or not, and the observed difference we saw was 30%. Okay. Now, thanks to the randomization process, the step 2 of randomly assigning the subject to the different groups, we can say that any observed difference between A and B can only be due to 2 things. Either random chance, for example, random chance in the assignment of the subjects to the 2 different groups, or to a true difference between A and B. Okay. This option is kind of the null hypothesis, that A and B are not really different, and what we observe, the observed difference, is just due to random chance. This second option is what we call the alternative option, is that A and B are actually different. There's a real difference between A and B that leads to a significant difference in the results. Okay? So that's the concept of the null hypothesis. Let's just look at this first column for now. I'll talk about this one in a moment. The null hypothesis normally is that A and B are the same. There's no difference. The alternative hypothesis is the opposite. A and B are different. Okay. So what's hypothesis testing? The hypothesis testing is trying to answer the question of whether the random chance is to blame for the observed difference. So is random chance, the null hypothesis, a reasonable explanation of the observed difference or not? That's what we do through hypothesis testing. We are trying to determine if random chance alone is sufficient, is a reasonable explanation of the observed difference. If it is, then we stay with the null hypothesis that A and B are the same, there's no real difference. And if we conclude that it is not, then we can go back to the alternative hypothesis and say that yes, A and B are different. There's a statistically significant difference in our results. Okay? So through the A/B testing, through the hypothesis testing process, what we do is we assume that the null hypothesis is true, that A and B are the same. There's no significant difference between the 2 of them. Then we create a null model that represents the null hypothesis, create a probability model that represents the null hypothesis. Okay? And here is illustrated by this density plot, and I'll explain to you in detail how this is created. So this density plot represents the null model, the null hypothesis that A and B are the same. Okay? Once we have that null model, then we can test whether the observed difference is a reasonable outcome of that null model or not, if the observed difference is within the random variability of that model. If it is, then we keep the null hypothesis. If the observed difference is not within the random variability of that model, meaning if the observed difference is too extreme as compared with the random variation of the model, the null model, then we say that we can ignore the null hypothesis and we can keep the alternative hypothesis. So this chart, I will explain in detail how it is created. But for now, this curve, the curve itself represents the probability distribution of the null model, being the probability model that represents the null hypothesis being true, that A and B are the same. There's no real difference between them. In red, in solid red, what we have here is the 30% observed difference. Okay, and in the dashed red, what we have is minus 30%. So the negative, the opposite value of the observed difference. In orange, the area in orange is we're going to understand that the area in orange is the p-value, because it represents the area of the values that are larger, more extreme than the observed difference. So the observed difference was here at 30%. All of these values are larger than the observed difference. So those are the values that are more extreme than the observed difference on both ends, right? If the observed difference is 30%, we want the extreme values to be the values above 30%, but also the values below minus 30%. And that's what the two-way hypothesis test is looking at both sides of the distribution, at both sides of the extreme values that are larger than the observed difference, but also smaller than the negative value of that observed difference. That's what two-way hypothesis test is by looking at both ends, the extremes, at both extremes of the null hypothesis model. Okay? And the p-value itself is the area under the curve. So the area that represents all the values that are more extreme than the observed difference. And in this case is 0.37, so it's a very large p-value. We'll see in detail how this is created, okay? But just to show you that what's involved, what's kind of the process of hypothesis testing. So hypothesis testing, let's take a step back. We need to determine if the observed difference of 30% between A and B is statistically significant or not. Now, thanks to randomization, we know that any observed difference between A and B can only be due to two things: random chance or a true difference between A and B. We can use hypothesis testing to determine if the difference is due to random chance or not. And through that, then we can conclude if random chance is the reason, or if it's not, then we can say that there's a true difference between A and B. And the hypothesis testing process is we assume the null hypothesis is true, we create the null model, the probability model that represents that null hypothesis, which is this curve here. And then given that null model, we look at the observed value, which in this case was 30%, and we look at the values that are as extreme or more to compute the p-value. Okay? To see how many of the values in our null model are as extreme or more extreme than what we observed. If there are many more extreme values, then or the observed value is not so extreme and it's within the variation of the null model, and we have to keep the null hypothesis. If the value that we observed is very extreme as compared to all the others, then we can reject the null hypothesis and we can keep the alternative hypothesis that A and B is different. There's a little difference between A and B. Okay. So we're going to go in more detail how this is done and how we actually compute the p-value. Just to let you know that there is what's also a one-way hypothesis test. This is the two-way where we look at the two sides of the extreme values. The one way would be just looking at the one side. In this case, looking at just at this side to determine if the difference is significant or not. And on the two-way test, what we are looking is to see if the hypotheses A and B are the same or different. On the one-way test, we are trying to check if A is better than B or not. So the null hypothesis is that no, A is not better than B. So A is either smaller or at least as good as B. The alternative hypothesis is that A is better. So A is larger than B. Okay? So that's the difference between the two-way hypothesis testing and the one-way hypothesis testing. In the two-way hypothesis testing, the null hypothesis is that A and B are the same, and the alternative is that no, they are different. And the one-way hypothesis test, we are trying to check if one hypothesis is better than the other, not just if they are different. In this case, we are trying to check if A is better than the other. So in that case, the null hypothesis is A is not better, so it's either worse or at most the same. And the alternative hypothesis is that A is better, so represented here by A being greater. That's the difference between the two-way hypothesis test and the one-way hypothesis test. Moving forward, we'll just be representing the two-way hypothesis test, but you can see what the difference is in here. When we get to the coding session, I'll also show you how to do the one-way hypothesis test. But what comes next, we'll focus more on the two-way hypothesis test. So we have this representation looking at both sides of the extremes. Okay. All right. Let me just take a quick check. The slides will be available, yes. Right. Okay. So now the concept of the p-value. So it's a concept that is often very confusing. And what's the meaning of the p-value? Okay. So the p-value, as I told before, is kind of the area represented here in orange. And the p-value represents the proportion of values in our null model that are as extreme or more extreme than the observed difference. So often people define the p-value as the probability of obtaining results as extreme as the observed result. That alone is not sufficient to define the p-value. So the p-value is defined based on the null model that represents the null hypothesis. So kind of the full definition of the p-value is that given the random chance, the probability model that represents the null hypothesis, the p-value is the probability of obtaining results that are as extreme as the observed result. So the p-value is this area here in orange that represents the values that are as extreme or more extreme than the observed difference for that representation of the null hypothesis, for this distribution, this probability model that represents the null hypothesis. Okay. Now the question becomes, how do we find this null model? And we're going to see that we can use a permutation test to find this distribution, this null model. Okay. Another concept important in hypothesis testing is the concept of significance level, often called alpha. Okay. And it's the threshold probability of kind of unusualness. So how much are we allowed to, how much unusualness or extremeness are we allowing in our test? Often is used as 0.05, meaning we allow for 5%. Okay? And this is one of the things that must be defined in that step 0 when we are defining the A/B test itself. How are we going to do it? What's the A/B test and how it's going to be done? In that step 0, you need to define what's going to be your significance level. Okay? Often we use 0.05. And for all practical purposes, we'll be using here 0.05. So let's say that we did the A/B test, we did the hypothesis testing, and we got the p-value. And now, how do we decide if the difference is significant or not? I'm still going to show you in more detail how we actually compute the p-value and how do we get to this model. Okay? But let me just tell you in advance how the decision is made once we did the hypothesis testing and we found the p-value. Okay? So given a significance level, alpha, usually 0.05, meaning 5% threshold, that is defined in the very beginning when you define the A/B test itself before you even do it. If the p-value is larger or the same as alpha, then we have to retain the null hypothesis and we have to conclude that the observed difference is due to random chance. Okay? If the p-value is smaller than alpha, that threshold, we reject the null hypothesis and we can conclude that the observed difference is real. There's a real significant difference between the two options A and B. Okay? So essentially, if this area here in orange that represents the p-value is larger than the alpha threshold, which often is 0.05, then we have to retain the null hypothesis and we have to conclude that the difference that we observe is just due to random chance. In this case, the p-value is 0.37. You can see that 0.37 is much larger than 0.05. So in this case, this would be the decision. We have to retain the null hypothesis. We conclude that the difference is just due to random chance. If this area in orange is very small, and which returns a very small p-value, meaning a particular p-value that's smaller than 0.05, then we could conclude, we could reject the null hypothesis, and we could conclude that there is a real difference between A and B, and that the difference is significant, statistically significant. Okay. All right. So those are the concepts that the main concepts I wanted to cover about what's hypothesis testing, what's the p-value, and the significance level, and how the decision is made. Now, this is certainly not a perfect. This hypothesis is certainly not perfect, and one can make errors even by following the process. But by setting, for example, the significance level, we are setting kind of the threshold of the error that we are allowing ourselves to make. Okay, often 0.05, and you will see that this alpha is the probability of making this type 1 error. The type 1 error is a false positive. What does that mean? Is when we mistakenly conclude that there is an effect, that the difference is significant, when it actually is not. It's just due to chance. So a false positive is concluding that the difference we observed was significant, was real. There was a real difference between A and B, when in reality, there was not. The difference was just due to chance. That's a type 1 error or a false positive. And alpha, the parameter alpha, represents the probability of making that type 1 error. Okay, so there is the opposite type of error, the type 2 error, which is a false negative, is when we mistakenly, when we conclude that the difference that we observed was due to chance, when in reality there was a real difference. It was really due to a real difference between A and B. Okay, so we can make these types of different types of errors when we're doing the hypothesis testing. Okay, and the 0.05 is the probability of actually making a type 1 error, the alpha level. Okay, I just want to mention these ones. We'll not be talking more about this for the rest of the workshop, but I thought it would be a good added bonus for this workshop. We're going to focus on how, now moving forward, we're going to focus how do we determine this null model, this curve, and how do we get the p-value from the curve. Okay. All right. We're going to use a permutation test to do the hypothesis testing. So what is and why do we use a permutation test? So permutation test is a resampling procedure that is often used for hypothesis testing, and we'll go into the details. So what's resampling? Resampling is the process of repeatedly sample the values from the observed data, in our case, the observed data of A/B testing, to determine the variability within a statistic. In our case, we want to determine the variability, the random variability within our test statistic, which is the difference between A and B. Okay. There are two main types of resampling, and you may have heard about them. Bootstrapping. Bootstrapping is resampling with replacement, and it's often used for assessing the reliability of an estimate for a model. And permutation. Permutation is resampling done without replacement. So when you are in a resampling procedure, you can imagine that you have all your data in a bag, and you are taking the data out of the bag. So in permutation, as you take the data out of the bag, you don't put it back in. When you do bootstrapping, you take the data out of the bag, you look at it, you write it down, and then you put it back so it can be picked again in the next round. Okay? So that's the main difference between bootstrapping and permutation. Here we're going to focus on permutation because that's the one that is used for hypothesis testing. And it's resampling without replacement. So if you have your bag with all your data, you take the data, you look at it, and you don't put it back. Okay? So you just keep taking all the data and looking at it until you are without data. Okay? So in summary, what's a permutation test? Is a resampling procedure used for hypothesis testing, and that's what we're going to use now. In more detail is the process of combining different data samples, like the two data samples that we have in A/B testing, the A and B. We combine them together so that then we can reallocate that data into different resamples of those groups A and B, and use those resamples to determine the random variation of the test statistic. We're going to cover this in more detail step by step, but that's what the permutation test is in more detail. In practice is a way of creating the null model, the model that represents the null hypothesis that then lets us compute the p-value for doing the hypothesis testing. Okay. There is one big advantage in doing a permutation test and not doing, for example, like a t-test or other theoretical statistical tests, is that the permutation test does not make as many assumptions or no assumptions as compared to, for example, doing a t-test. So permutation test makes no assumptions, creates the null model that represents the null hypothesis directly from the data itself. That's a big advantage. And there's an historical note is that the permutation test is computationally intensive, right? In the past, when statisticians had no computers, they couldn't do this as easily, right? We're gonna do like 100 permutations, 1,000 permutations, or even more permutations. They would have to do that by hand if they didn't have computers. So that's why they had to develop those statistical theory and those statistical tests to do the hypothesis testing in a more rapid manner. Okay. Now that we have all this computational power, permutation test is a good way of doing hypothesis testing because, well, we have the computational power to do it. It's possible for us to do it now. And the permutation test makes no assumptions about the data. It uses about the distribution of the data, the distribution of the population. It uses the data itself from the sample that we have to create the null model that represents the null hypothesis. Okay, so that's an important advantage of the permutation test, and one of the reasons why we have all this theory with all these tests like a t-test that we can use. That in the past they couldn't do a permutation test as easily because it's very computationally intensive. Okay. All right. So how is the permutation test done? Again, we're going to break down the process into individual steps. Okay. Step 0, before we even do the permutation test, we need to have the A/B test results. In this case, we have our A/B test results. This first representation here is we have the results for A, where we have 7 successes, 7 green balls, and 3 reds. And the B, group B, we had 4 green balls, and the rest are reds. So we had, from the A/B test results that we just checked, we had 70% yes rate or success rate for A, 40% yes rate or success rate for B, and the difference between A and B was 30%. And now we want to determine if this 30% is statistically significant or not. Okay, so this is our step 0. We have our A/B test results. Now, the step 1, the first step in a permutation test is to actually get the results from these two, from the A/B test, from group A and group B, and put them together in a single data set, in a bag, if you will. Okay, so that's what we are doing here. All those results that were separate in group A and group B, we're just going to put them all together in a single data set. I'm going to call it the bag where we're going to do the resampling from. Okay, that's step 1. Now, there's a sequence of steps 2 to 5, which is actually the way of doing just one permutation. For the permutation test, we want to do many permutations, but we're just going to see first how to do one permutation. So the way of doing one permutation, I'm doing it here all in one go. So this third part is the steps 2 to 5. Is first we have to shuffle the bag. You see that I actually put the results here in an ordered fashion, so you could see that they're actually the 11 yeses that we got from both groups, and then the remaining 9 no's that we got from both groups. Now, to do the permutation, first thing we have to shuffle the bag, shuffle the data, and then that's step 2. Step 3 is to randomly draw a sample of the size for the group A, and then one for the size of group B. And step 5 in the end is to compute the statistics again for those resamples. I'm doing that all in one go. So that's the resampling, okay? And then we just split the resample data. Sorry. This is the randomization. We are shuffling the bag, and then we're just splitting in half so that we have 10 for the group A and 10 for the group B. For simplicity here, we are using the group A and group B with the same number of individuals, like 10 in each, but you can have different number of individuals in the different groups. Again, for simplicity, just using the same numbers. Also, so that they are round numbers and we can easily do the maths in our head. Okay. So step 1 is from all the data in A and B, we put it together in a single data set. Okay. Then step 2, we shuffle the bag. Step 3 is from that shuffle bag, we take a resample for group A, which is represented here as this lower half. And then step 4, you take the rest, in this case, the resample for group B. So because the resample is without replacement, if we take this resample for group A, these ones will be out, and then we'll be left only with these ones, which is just the remainder in the bag. That's going to be for group B, because we have just 2 groups. If you had more groups, you'd have to do the resample for one group first, and then for the second group, and then for the third group, and so on. And the last group is the remainder in the bag again. Okay. So that's how you do one single permutation. And now notice here that when we did this permutation, then we compute the results for the resamples that we got for group A and group B. In this case, group A got 5 yeses and 5 no's. So the yes rate, the success rate was 50%. And group B got 6 yeses and 4 no's. So the yes rate was 60%. And the difference now between A and B, A minus B, is minus 10, because it's 50 minus 60. Okay, that's minus 10%. So the observed difference from our A/B test was 30%. Now we did one permutation, and we saw that the resample difference from the one permutation is in the test statistic is minus 10%. So you can see how we can get new values for our test statistic by doing permutations. Okay, this was just one permutation. We got one different value, a new value for our test statistic. Now the process of doing the permutation test is actually, when we get here to step 6, is to do these many permutations, do these over and over. Okay. Here they're always going to give you the same result, so that you can see what's happening. But when you do this randomly, you're going to get different results here. So you're going to get different resamples in A, different resamples in B, so different success rates for A, different success rates for B, and then overall you're going to have a different difference for A minus B. So that's what the permutation test is doing many permutations, so that in each permutation you get a new value for a test statistic, and then you can use all those new values for the test statistic to create the null model, the probability model that represents the null hypothesis of A and B not being different, of A and B being the same. Okay. All right. So then the hypothesis testing will be using those results of those many permutations to compute the p-value, and the p-value is going to be the ratio of values that we get from the permutations that are as extreme or more extreme than the observed. So we're going to get many values here for the hypothesis, for the test statistic. In this case, it was -10. When we do it again, it's going to be a different value, and then a different value, and so on and so forth. We're going to get many values. In the end, we're going to compare all these many values with, or we're going to compare our observed value of 30% with all those many values and see how extreme is this 30% compared with all those many values that we can get through permutations. If this one is very extreme compared with all the others, then we can say there's a real difference between A and B. If this is not very extreme, is within the random variation of all the many values we get here, then we have to retain the null hypothesis and say there's no real difference between A and B. Okay. Right. So yet again, I just want to show you a different perspective of this process. Okay. Again, the perspective of a single individual. Again, we don't follow single individuals through the A/B testing or the permutation test, but just so you understand better the process. So this was the A/B test results, kind of our step 0, and that result was assigned, put in the bag with all the other results. And then when we did the resample, was assigned to A, and it was a yes, because this was always a yes. Okay, so we keep the yeses as yes, and we keep the no's as no's. We just reassign them to different groups now, randomly. So that, for example, that one we put in the bag, and originally was in group A, and when we did the resampling, it went to group B, and so on and so forth. So that one went to group A, and that one was in group A, and when we did the resampling, was assigned to group B, and so on and so forth. So you can like see the last ones. Okay, this one was in group B. When we did the resampling, ended up in group A. Okay, so that's just to give you a different perspective of how the process is done, kind of a perspective of the results from individual subjects. It's not that we need to track them, it's just so you better understand the process. Right. This text is the exact same as before. It's just the different steps that I covered already. Okay. So, all right. Now, how do we do the hypothesis testing once we have the results? So remember, our observed difference in our A/B test result was 30%. Okay, it's 7. We'll finish the workshop. It's okay. Now we want to determine if this 30% is statistically significant or not. Okay, so I did 100 permutations. Okay, I did this process 100 times. One time I got -10, then I'm going to do it another time, and I may get -10 or a different value, and so on and so forth. I'm going to do it 100 times. And then I'm going to count the values that I got. Okay? So I did 100 permutations, okay, of that process that I illustrated before, and these are the results I got. 4 times I got the value -50 for the test statistic. 12 times I got the value -30. 30 times I got the values -10. 33 times I got the value 10. 16 times I got the value 30, and 5 times I got the value 50. Now, these is the results that we got for the 100 permutations. Okay, and what I want to know is, this is the observed difference in the A/B test itself. I want to know if this observed difference of 30% is very extreme as compared with the results that I got from the permutations. Another way of representing this table of counts is just by doing this bar chart. This bar chart is representing that table, the same information. So you'll see that for the value -50, the bar goes up to 4 because we got the -50 value 4 times. For the value -30, the bar goes up to 12 because we got the value -30 12 times. For -10, the bar goes up to 30, and for the value 10, the bar goes up to 33. For value 30, it goes up to 16, and for the value 50, it goes up to 5. So this is the table counts of the 100 permutations that we got, and here's the bar chart representation. Now, this is to provide you a graphical representation of our hypothesis testing. We want to know if what are of all these values that we got to the permutation test, how many of them are as extreme or more extreme than the observed difference of 30%. Okay? So for the two-way hypothesis test, we had that the null hypothesis was that there's no difference between A and B. A and B are the same. So the alternative hypothesis that there's actually a difference between A and B. A and B are different. So we want to determine what are the extreme values as compared to the observed difference of 30%. From all these counts, what are from all the observed, the results of the permutations, what are the values that are as extreme or more extreme than 30%? Okay, so 50 is certainly more extreme than 30%. So we're going to count these five examples of more extreme values. 30 is as extreme as 30%. So we're going to count the 16 values. Okay, so 5 plus 16 minus 30 is also as extreme as 30%. So we're going to count these 12. These 12. And minus 50 is more extreme than 30. So we're going to count these 4. So the number of values that are as extreme or more extreme than 30%, okay, on both ends for negative and positive values are these 4 plus these 12 plus these 16 plus these 5. And that is 37. Okay, so in our permutation results, we got 37 values that are as extreme or more extreme than the observed difference in our A/B test of 30%. Okay, so the count of extreme values is 37. The p-value now is just the ratio of the number of extreme values by the total number of permutations. So the p-value becomes 0.37 because it's 37 divided by 100. 37 is the number of values that are as extreme or more extreme than the 30% observed in the A/B testing. 100 is the number of permutations that we did. Okay? So this is how you compute the p-value through a permutation test. Okay? And that's how we get to the 0.37 here, the p-value. And that is represented here graphically by the orange color. So the 30 and the 50 and the minus 30 and the minus 50 are all values that are as extreme or more extreme than the observed difference of 30% in the A/B test result. So those count for the p-value. Okay? These ones do not count because they are less extreme than the observed difference. Okay? So this is kind of just the bar chart representation where you have the counts. And this is the probability, the density graph representation of this same bar chart. Okay? That's the two-way hypothesis test. The one-way, we're just looking at one side. In this case, we are just looking at the positive side. How many of the positive values that we got are as extreme or more extreme than the 30%? In this case, just the 16, that is as extreme as 30, and the 5. Okay, so the number of extreme values for the one-way hypothesis test is just 21 because it's the 16 plus 5. And the p-value becomes 21 divided by 100, and that's 0.21. Okay? So for the one-way hypothesis test, the p-value would be 0.21. Okay? So what would be the decision? For both cases, actually, the p-value is very large. 0.37 and 0.21 is larger than alpha that we normally consider 0.05. So we have to retain the null hypothesis, and we have to conclude that the observed difference is just due to random chance. There's no real difference between the groups A and B. Okay. So we went through all the process of doing the permutation test. We have the graphical representation here of what the p-value means. This is just with the bar chart with the counts. This is a density plot representation of that same chart. And in this case, the bar chart, the total area of the bars or the total size of the bars represents the size of the bars add up to 100, which is the number of permutations, and the counts of the orange ones represent the number of extreme values, which is 37. And then the p-value becomes just the ratio of 37, the extreme value counts, by the total number of permutations. Here, this is a density plot. The area under the curve is 1 as the total probability, and the area in orange is also probability, is the p-value. That's the probability of finding values that are as extreme or more extreme than the observed one, the 30% observed in the A/B test. Right. So now we come to the coding part. How could we code this in R? Okay. So let's see where we are at. We can still go on and finish the session. So that covered all the concepts, and we went through the A/B test process, and then the permutation test process for how to do the hypothesis testing, and understanding the p-value as kind of the ratio of extreme values in a permutation test, and the probability of finding values that are as extreme or more extreme than the observed value in the null model. And the null model, this probability model, is found through the permutation test process. Okay? So we could do this with code. So here we have some R code where we're just assigning values to some variables. So T is going to be the total number of subjects, both in A and B. And we're going to keep going with that example. Then we'll see a more example with larger numbers after this. We have total number of 20 subjects. 10 of them go to the group A, and 10 of them go to group B. And our A/B test result got us 7 yeses in the group A and 4 yeses in group B. So here we're just assigning values to variables, so that then we can use it afterwards. Okay. Then these variables alone define the A/B test completely, and then we can use those values, those variables, to compute all the other results. So if you want to know the number of no's in A, that's just A, the total number of subjects in A, minus the total number of yeses in A minus a yes. Okay. The same for B. If you want to get the total number of yeses, that's going to be the AS plus BS, because AS is the number of yeses in A, and BS is the number of yeses in B. Okay. The same for TNO. And if you want the percentage of yeses in A, we compute that as the ratio of all the yeses in A divided by total number of subjects in A, multiplied by 100 to get the percentage. The same for B. And then we can compute our test statistic, which is the difference between A and B in terms of the difference in the yes percent rate. So we can compute that as the AS percent rate minus the BS percent rate. And at the end, I'm printing this here so we can confirm that it's correct as we saw before in the example before. So the yes percent rate for A is 70%. The yes percent rate for B is 40%. The difference, 70 minus 40, is 30%. Okay. And additionally, I'm also showing here what are the total counts in terms of the total number of yeses is 11, because it's 7 plus 4. And the total number of no's is the remainder, 9. Okay. We're going to use these numbers to do the permutation test next. Okay. So this is how you could do one permutation using R, okay, from scratch, without using any other functions. Just setting the seed to make these results reproducible, because we're going to use some random functions. Okay, that's just to make the results reproducible. That there's no concepts in there. So if you recall, the first step in a permutation test is to actually combine all the results of the A/B test, both A and B, into a single data set, kind of a bag. And we can do that by using these notations. So here we are repeating the number 1 a number of TS times. So TS is the total number of yeses in both groups, and then repeating the number 0 a total number of TNO times. And TNO is the total number of no's in both groups. So bag 1 is going to be a vector of 1s and 0s, where it's going to have as many 1s as there are yeses in our data, and as many 0s as there are no's in our data. So 1 represents yes, 0 represents no. Okay, and you can actually see here what's the bag bag 1. Okay, step 1, I'm printing it here, is a sequence of 1s, actually 11 1s, because that's the number of yeses, followed by a sequence of 9 zeros. Okay, so bag 1 is just a vector of 1s and 0s. The number of 1s and the number of 0s determined by the A/B test result. Okay, the combined results of both A and B. Okay. The step 2 is to shuffle the bag. So use the sample function to do the shuffling, to produce a random sample of the parameter that we provide to the function. Okay, so it provides the bag 1, which is a very ordered vector of 1s and 0s. Sample is going to return us a random sample of that vector, and what you get is this, the shuffled bag. So we're getting here bag 2. Now you can see that the 1s and 0s have been shuffled. So that's step 2. Step 3 is to, from that sampled bag, get a random sample of size A. Okay? So we can just get the first A, and A is the number of elements in the group A. And we're going to get this first A, okay? as being the resample for group A. And that's what we get here. Okay. And then we get the remainder as the resample for group B. So we're going to get the remainder, these ones, okay, from A plus 1 up to A plus B. So these we are using index notation to select the elements of a vector. Here, first select the elements from 1 to A. So R starts counting at 1, the index starts counting at 1, while, for example, Python starts counting at 0. Okay, so here we are selecting the first A elements to be the resample for A, and then the elements from A plus 1 to the end, which is A plus B, is going to be the resample for B. So the first A elements are going to be the resample for A. You can see they are the exact values, and then the remainder, these elements are going to be the resample for B, and you can see they are the exact same values. Now that we have both resamples, we can compute the results, the yes percent for that resample. Again, the sum of all the values of all in the A resample, because the ones represent yes. So when we sum, all the ones are going to be all the yeses. The zeros are just going to add up to 0. And then we divide by the total number of subjects in the group A, and the same for B. We sum the B resample. We are summing the ones that represent yeses, and then we divide by B. That's the total number of subjects in B. So we get the yes percent rate for the resample, in A, and the yes percent rate for the resample in B. And then we can compute our test statistic, which is the difference of those yes percent rates of A minus B. And now we get a new value for our test statistic. Okay. So here we obtained, you can see that the A resample has 1, 2, 3, 4, 5 ones. That's a 50% yes rate. And then the B resample has 1, 2, 3, 4, 5, 6 yeses. And that's going to be a 60% yes rate. And the difference, our test statistic, which is the difference between A and B, is going to be 50 minus 60, and that's going to be minus 10. And as a reminder, the observed difference of our A/B test result was a 30%. Okay, so you can see how through one permutation we got a new value for the test statistic, in this case minus 10, and which compares with what was the original observed value for the A/B test result. And now what we have to do is do this process many, many times to get many, many values, so that then we can compare the 30 with it. Okay. So this is how you can do one permutation. Essentially, the code you need is just this code to do the one permutation. Okay. This is just to print nicely, so we can easily see the results. And now the next step is to actually do many permutations. And how can we do many permutations? Well, we are repeating the same operation many, many times. We can use a loop. And in particular, can use a for loop, and this is the syntax for a for loop in R. So again, we are setting the seed to make the results reproducible, because we are using random functions here, like in particular the sample function. So we can put again all the results of A/B testing in a bag. It's kind of our step one. Put all the results of both A and B in a single data set. I'm calling it a bag because we're going to resample the data from. And our step 6 is going to be repeating that step 2 to 5, the one that we did just before, of doing one permutation. Going to do many permutations, and in this case we're going to do 100 permutations. So P is the number of permutations, and I'm setting here a vector of zeros where we're going to hold the results of those permutations. Okay, so we're going to do a for loop. Again, it's a loop lets us repeat the same operation many, many times. In this case, we're going to repeat the same operation using index I from 1 up to P. So it's going to be 1. I is going to take the values of 1, 2, 3, 4, and so on and so forth up to 100, because P is the number of permutations, and we are doing P equals to 100 for doing 100 permutations. So the step 1 is already done, putting everything together in a bag. Step 2, shuffle the bag. So we're going to use the sample function to sample the bag, to shuffle the bag. Step 3, get a random sample of size A. So the same thing as we did before, get the first A elements to be the resample for A. Step 4, get a sample for size B, get the remainder of the values in the bag. They're going to be the sample for size B, for group B. And then step 5, compute the test statistic. Okay, so here I'm doing it just in one step. Before we did in these in individual steps, but basically we are doing here just computing the percentage rate for A, and then the percentage rate for B, and our test statistic is the difference between the percentage yes rate for A minus the percentage yes rate for B. Okay, so this for loop is going to execute this operation 100 times, and at the end, our permutation result variable is going to contain 100 values from those 100 permutations, and these are those 100 values. So first got 10, then minus 10, then 10, then minus 30, then minus 10, and so on and so forth. You can see these are the 100 values for our test statistic that we got through the permutation test. Okay. And now the goal is to compare the observed test statistic of 30% with all these values. And to make that, it's convenient to just do a table or results, and you can do that with a table function. And this is the table that I showed you before. So we got the value in all these values. We have the value minus 50 4 times, the value minus 30 12 times, and so on and so forth. Okay. And now we can use this to compute the p-value, both for the two-way and the one-way hypothesis test. Okay. So again, the number of permutations was 100, and we can find the extreme count as the number of values that we got in the permutation result that are larger or equal to our observed result. So the ABS percent is the observed result of 30%. And here what you are doing is selecting all the values in the permutation result, all the values here. We are selecting all the values here that are larger or equal in absolute value to the observed 30%. And then we can sum those. So that's going to return, this is going to return true or false for each of those values. And when we sum, we're going to get the count of the number of values that satisfy that condition as being larger or equal to the observed difference. Okay, so that's how we can do the extreme count for the two-way hypothesis test. And then the extreme ratio is just the extreme count divided by the number of permutations, and this is going to be the p-value. For the one-way hypothesis test, we just want to look at one side. So we just want the values in the permutation result that are larger or equal than the observed statistic. Okay? Here we don't use the absolute, so we use the absolute to look both at positive and negative values. Here we don't use it, so we're just looking at positive values. And again, the extreme ratio is going to be the p-value, is just going to be that count divided by the number of permutations. And in the end, we find out that the extreme values count for the two-way hypothesis testing, so for the two sides, is going to be this 16 plus 5 plus this 4 plus 12. It's going to be 37, as we saw before. And the p-value is going to be 0.37, which is the 37 divided by 100. Okay? And then the one-way hypothesis test is just look at the positive values. It's going to have the 16 plus 5, that's 21. And the p-value is going to be the 21 divided by 100, which is 0.21. Okay? So that's how you can compute the p-value kind of from scratch doing the permutation test. And this is, again, the graphical representation. Just if you did not understand this one very well yet, I'm just going to show you a few more charts that may help you understand this better. So we got these permutation results, and we got kind of the tabulation of those results. And this is the density plot of those results. Here we have a bar chart, just the counts. So the minus 50 appears 4 times, then the bar goes as a height of 4, and so on and so forth. And the total sum of all these heights gives you the number of permutations, and the p-value is going to be the ratio of the counts for the extreme bars divided by the total number of permutations. So it's 37 divided by 100 gives the p-value of 0.37. You can do a bar chart instead of counts as being the density, where the height of each bar is not the count, but the count divided by the number of permutations. This way, the sum of all the heights is going to sum up to 1, and that's also the concept of probability. And then the sum of the bars that are extreme give you a probability as well. So if you are looking at the density version of the bar chart, this already has a meaning of probability, because the total sum of all the bars is 1, the total probability, and then the sum of the bars that represent the values that are as extreme or more represent the p-value itself. Okay. Now, I just want to add a note. So, and this again is the kind of the smooth version of this bar chart, which is the density plot version of it. And the area under this curve is 1, and the area in orange is the p-value. Okay. Now, here I use the bar chart because our example has very small numbers, and we only get a few different values in our permutation test. Normally, keep in mind that your test statistic is actually going to be a more continuous variable. In that case, you should not be using a bar chart. You should be using an histogram chart. Okay, so keep in mind that in the general case, you're going to have a test statistic that is a more continuous variable. It's not such a simple case like this didactic case that we are using here to understand all the steps. So in the general case, you want to use an histogram like this instead of the bar chart. But in the end, you can always compute the density plot, And you can see again that the density plot is just a smooth version of this histogram plot. Again, the histogram plot can, you can have the histogram as counts. Again, the same counts. 4 is the height of this bar, and so on and so forth. While you can also have the histogram version as the density. And the density represents also the concept of probability. The sum of all the heights of these bars adds up to 1, which is the total probability. And the sum of the bars that are the values as extreme or more give you the p-value. Now, this is not a very good example because for our didactic example, because it's not such a continuous variable. We only had a few different values. We only had like these different values for our test statistic, right? Only 6 different values. That's why it's not well represented in histogram. But that's why it was better to represent with a bar chart as I did here before. Okay, just want to let you know that in general, your test statistic is often a continuous variable, and you want to use an histogram, not a bar chart. Okay, but in both cases, you can always just represent the density plot, and this representation works for both cases. Okay, so moving forward, I'll just be using the density plot. I just want to give you the warning that in general, you should use an histogram and not a bar chart. Right. So finally, we went into detail of how to code this from scratch without using any other functions. So now what I did here, I'm going to look at the more general solution. I put all that code that we created into functions in a script, and I'm loading that script using source. And now I can use the functions that I created to quickly compute the result in just one line. So for example, I have here I created the AB permutation test function that does all this process that we described for us in one line. We just need to provide the parameters that define the AB test. So the AL is the number of subjects in A, the BAL is the total number of subjects in B, the AS is the number of yeses in A, the BS is the number of yeses in B, and NP is the number of permutations. Okay, these are just some optional parameters to provide some messages and to set random seeds so we make this reproducible. Okay, so in this one line, we now can do everything that we did up until here in detail from scratch. Okay, basically this function includes all the code that we created up until here. So the first, it prints a message saying, okay, these are do you define the A/B test result with these parameters? Here is kind of the summary of that A/B test. The yes % rate is the same example as before, and I'm going to show a different example in a moment. Yeah, the 70% yes % rate for A, 40% yes % rate for B, and the A minus B is 30%. So this is kind of the observed difference between A and B from our A/B test. It computes the whole permutation test, and it prints out the density plot where it tells us how many permutations it did, what were the extreme count values, in this case was 36, and the p-value, which is the extreme count divided by number of permutations, 0.36. And it highlights here in orange what are the area of that correspond to the p-values. Here it tells you that the observed difference was 30%, which is this 30%, and it returns, the function itself returns the p-value, which is 0.36. So now you can use this function just in one line to, again, do for a different example. For example, if you want to do a more realistic example with larger numbers, while still keeping them round numbers so we can also do the computation in our head. Suppose we had 1,000 subjects in A, 2,000 subjects in B, and we had 30 yeses in A, 30 yeses in those 1,000, and 100 yeses in B, 100 in those 2,000. So this is an example where the number of subjects in A and B is different. They are not the same. It can happen depending on what type of problem you have, that you may end up with different number of subjects in the groups. So what is the yes rate for A is 30 divided by 1,000, which is 3%. Okay, and what's the yes rate for B is 100 divided by 2,000, which is 5%. And what's the test statistic? Again, defined the same as A minus B, is 3 minus 5, which is minus 2%. So the observed difference here is minus 2%. This is a much smaller difference than the one we looked at before. This is a kind of a more realistic example. And often in even more larger numbers, you may have even smaller differences between the two groups. And you want to determine if those differences are significant or not. Why could you be interested in a small difference? Well, imagine if you have a large volume business, like for example, that the search engine, the big search engine, any small improvement could lead to an important improvement in profits, right? If it is a very large volume business, a small difference because of the large volume could lead to a high improvement in the profit, absolute dollars, for example. Okay. So in this case, we did actually 1,000 permutations, and this is the result we got. We got from in this example only 18 values are as extreme or more extreme than the observed difference of -2%. You can see the orange areas are very small here, okay, on both sides. Again, doing the two-way hypothesis test, and the p-value is 0.018. Okay, so this p-value is very small, smaller than the usual significance level alpha of 0.05. So here we would say there's a significant difference between the two groups A and B. We'd reject the null hypothesis and would accept that the difference is real. There's a real difference between A and B, and the difference is statistically significant. So this is an example where the difference is not significant. It's just due to random chance because the p-value is so large. And this is an example where the p-value is very small, much smaller than 0.05. And we can conclude that we can reject the null hypothesis, and we can conclude that there is a real difference between A and B. Okay? All right. So just a final thing, now that we put the code into this script, and we have this function that does everything for us in one step, we could, for example, create our Shiny app that lets us play with these concepts more interactively. And that's what I'm going to show you as the last thing. Okay. So just briefly, I'm going to show you the app running. Okay. Here we go. All right. So here you get again the same result. There's an additional thing with a more detailed table of the A/B test results, of the observed results. But this is the same graphic as we have been seeing all along. And now here you can change. So we have 100 subjects in A, we have 30 yeses in A, 100 subjects in B, 20 subjects in B, and 100 permutations. So now you can very easily change these. So for example, imagine if you, instead of 100 permutations, you want to do 1,000, change this from 100 to 1,000, and there you go, 1,000 permutations in slightly different result. Okay? If you want to change, say, from 35 to, for example, 33, we get a different result. Okay? So this dynamically updates the results as you change the parameters of the A/B test. So this is kind of a interactive app that you could use to very quickly check the results, if your A/B test results are statistically significant or not, by doing permutation test. And you get here the summary results with the representation of the null model and the array representing the p-value. Okay. All right. So that's all I wanted to show you. Sorry, it took a little longer than expected.